Well, good morning, everyone. I think that bell meant it was 9 o'clock, so we should get started. Thank you for coming to day 2 of our data technology workshop. Yesterday, we kind of got the big picture on some of the needs for the engagement priorities for GEO, the SDGs, the Sendai framework, and the Paris Agreement. And then we looked at some of the needs of Earth observations across the work program for various initiatives. And today we're going to dive down into kind of a different tack. This morning we're going to take a look at in situ observations in this particular session. And I personally have been involved in taking in situ measurements for a number of years. When I was working on my master's degree in atmospheric science, I was part of the National Weather Service Observer Network in Fort Collins, so I went out every 2 hours when it was my shift and took temperature and evaporation and soil moisture and wind speed and direction and barometric and all this. So I kind of have a soft spot for in situ measurements. They're often held up as the kind of the gold standard for monitoring the Earth. But as we know, every measurement, no matter what it is prone to some kind of error, either instrument error or the observer doesn't do it just correctly. So maybe we'll be exploring some of those issues as we go forward today. One thing I need to remind you of, or maybe not even remind you, inform you of, and then I'll try and remind you again before the break, and that is that we're going to have a group photo taken just at the beginning of the break. So when we leave for the coffee break, I would ask you to go down to the rotunda, which is the big round area inside the building when you first walk in through those revolving doors. We'll meet there. That's where the photo will be taken. Okay, so please don't get your coffee first. Go downstairs first, and then we'll have our photo taken. Okay. Without further ado, I would like to introduce our first speaker here. And again, we're going to do like yesterday. We're going to have each of the speakers give their presentation in turn, roughly 15 minutes or so. And as questions arise in your mind, please feel free to use Slido. I'll be monitoring that here. Otherwise, at the end of the last presentation, we'll open up the floor, and we can also take questions from the floor. So Mikko Stralendorf from the Finnish Meteorological Institute is going to be speaking to us first this morning. He describes himself as a jack of all trades for service development in the field of weather, Earth observation, and related environmental information. His know-how spans from practical ITC systems with models connected to many observation systems up to the European programmatic level and Earth observation politics. And he represents Finland in the EU Copernicus Program Committee and in the Group on Earth Observations as Finland's GEO principal. He also networks his ideas across Europe and across the whole planet. So, Mikko, all yours.
Thank you very much, Doug, and very good morning to everyone. Nice to see many of you getting up early. So the topic I was to talk about was improving in situ metadata or something like that. I wanted to bring this more down to a kind of storyline and illustrate it better, so I changed the topic a little bit. So I'm illustrating it by an example of what I had to do this spring, or the beginning of this year, for Arctic observations. So it will be how in situ searching can be challenging, and then I do have the recommendation slides at the end, what could we do to make it better. But let's get, so here you see the point first, to see that in situ observations is not very simple definition. There's so much different things there, especially crowdsourcing. I have some slides for that to illustrate that then there's a lot of new stuff coming in, which is, again, not defined in our way of thinking before. Then I have a little bit of this, what I look for the Arctic in situ for. It's a value tree analysis. And then I will come to the recommendations and what we could maybe do from a GEO's point of view. So to illustrate what in situ can be, here's the Sodankylä supersite from the Finnish Meteorological Institute. So it's very high up in the north, so in the polar circle just above it. And it's just the history of this very long record place. And each year that we have added a new kind of network or instrumentation system to it, and data has been kind of new things have come on the timeline to be gotten from the same station. We are from Sodankylä also taking care of, for example, the Pallastunturi, so the GEO station there. So it's not just things at exactly that one spot, but it's, let's say, the Lapland special ops kind of activity. But you can see from pictures that there are some, let's say, very different from the traditional weather observations that are these, the middle picture where you have a kind of station 2 meters high in white wooden boxes, but it's also to send up balloons, to have a, like, I think that's the F-tier station, the TC-Con kind of station we have there, that someone is looking towards the sun and trying to see what the atmosphere has as composition in it. So there's really a very wide variety of data that we have to deal with when we talk about in situ. And the sensor data structure that we have there is a super non-standardized starting point. But I'm actually leaving to some of the sensor web enablement things that will be discussed later. But I wanted to just highlight that there's really the point that many devices come with very proprietary and their own systems, and how they put out something is in a kind of their way and not in a way that would be practical for the one who wants to manage all that data. So a lot of work has to be done to fix these things, especially most comes somehow in tabular data, where row and column naming is quite like unique to every single thing. There's not that much vocabulary that is similar, and even if the vocabulary would be similar, someone is using abbreviations in a certain way and someone in a different way. All of these things add to the fact that we do have a semantics question problem, vocabulary problem in there by definition, and then the solutions to this, there are a lot of standards out there, but they are quite sector specific. So if you want to go across different sectors, then you will at least, again, bump into some extra problems. And then I wanted to bring up the human as a sensor that Finnish Met Institute had now for a few years. I think for 2 years we have now had this kind of like crowdsourcing with our weather app. And that brings, again, some things that you would not consider from the experience we had with instrumentation and even humans doing as trained, let's say, observers in past times, that we wouldn't have had the same things like fake ops as pranks and all kinds of things that you then have to add actions for. So we really have a weather app that is downloaded almost 1 million times, but we do have like quite constantly almost 200,000, let's say, daily visits to it, so daily users. And we added the crowdsourcing to it so that we would have a lot of kind of like a lot of potential, let's say, people to add to this observation feature. It's just an icon on the top, and then you can see what you did with your own observations. It's a list of phenomena we want to capture. It's mainly for the fact that when there's extreme weathers, those happen to happen often somewhere else when there's a station, so we don't get all of that statistics well captured in Finland, a big country with not too many people, so we do have a lot of areas which are sparsely populated. That, of course, immediately also doesn't help with adding those, but at least it's much more observation that you could get. We also added one just like a boring thing, so no precipitation, or if there's precipitation, like do a quality analysis. But what we ask these observers to do is to have a kind of free text box that they can write something in. They can add a photo, but the main point is that we want to answer want them to answer a specific question where we have preset answer options so that they would categorize what they see. Yeah, but from that, this is the test period that we did for like a bit over a year. You can see that when you launch something, it's interesting. You have lots of, let's say, answers per day. So the axes are answers per day, and then the timeline on the bottom. And in some cases, when we had a severe thunderstorm, I added the one image to it. There you can see that you do get quite a nice, let's say, capture of this event when it goes across Finland, because the thunderstorm, of course, isn't just staying at one point, it's moving along, so you get a lot of observations from it. I think it was like 1,200 or something like that. So it helps and it adds to our observation networks. It's useful. But on average, it's just about 100 observations per day that you get. But we have these, it was even 1,600 almost. Yeah, that was the first when we launched, and immediately people tried to do something. That's the top one. But if it's not super good and interesting, the interest falls, as you can see. But still, when you have thunderstorms, you have gotten a certain amount of people who want to do that. But we have this point that now we have launched this at the Finnish Met Institute. We do know that, for example, the French Weather Service has a quite nice and much more actually actions on it kind of opportunity, which is almost similar, but then and in other countries we know about these as well. DWD in Germany wants to also start doing something, but the point is that we don't have standardized this set of what is it that they observe, how do they categorize. All of that is just like those wonderful in situ observations traditionally, that first it's whatever the one does, and then somehow we have to mix and put them together. But this is just to see that how does that picture compare to the standard observation networks that we have in at FMI. So on the right side, you would see that the network does have holes which were now filled, but in general, the whole country cannot be captured by this kind of crowdsourcing, at least not in Finland, where we don't have too many people in the north, and they can't be used all the time just for doing observations for us. But now to the Arctic in situ thing. So I really had to do this Arctic observations value tree analysis, and for that I had to find out where are there Arctic observation stations, what is it that they measure. So I did do this try, for example, on the GEO portal to see what do we have in our kind of GEOS infrastructure for these things. So just putting I defined the Arctic as something practical on the web. It's 60 degrees north and to the pole, North Pole. That's the area that I'm looking for these stations. And when you look at this, well, you can't read the records probably, but the one is a nice one from, I guess it was NOAA's kind of station list of weather stations. But then the next one was the fire brigade stations in the US. Well, not necessarily what I was looking for. And I did just an analysis when there were 12,000 records of the first 120 to get 1% analyzed. And really there was quite a lot of these. There were also TV transmitter stations or public transit stations somewhere in the States usually. Thank you very much for putting them there. Then a lot of GBIF records, which I thought nice, but for those I had also a problem that the links were not working. And I guess yesterday Letitia was explaining that they just changed so maybe it hasn't been yet, let's say, taken into, because I did this, again, the test for this slide last week. So some of these GBIF records didn't have a link that you go to and check what it is. And then one of the very critical problems, which is not just for the GEO portal, but when it comes to catalogs and services, that many times the bounding box is very simply just put as global, which in this case meant that my search finds all the different let's say services and data sets. And the problem then is, I can't, let's say, find actually relevant information because that data areas is not actually where I'm looking for. So to get a little faster, it's 5 minutes only. WMO was keeping a nice list for this observing system capability analysis, where there's just metadata about stations. So I pulled from there. Also, I used actually satellite data sets for this. But here you can see that they have networks defined. So stations are not just stations, they are somehow grouped into different classes. There's both meteorological and ocean stations. Nice for me, because this value tree analysis was actually meant only for physical atmosphere and for ocean, let's say, variables. So this is exactly what I needed here. So we did some estimation of what one station of each type would cost, and then we could actually extrapolate the whole thing to the value tree. This is how it then looks. Don't try to find out too much, but on the left side you have different Earth observation inputs, so both satellites and stations. For example, airports is the top one. So just the price was defined by my colleagues at FMI. For example, an airport station, I think it's something like 230 kilo euros a year. And the same methodology was used for others. Then you get up to this kind of point that all the EO inputs for the north of 60 area is 177.6 million euros per year. You could compare that, for example, for the 30 to 60 north layer, that there we have 810 million. So it's about 5 times more that we do in the developed world for an observation system. There's also the modeling, reanalysis, numerical weather prediction. All those steps are in between to the right side to get to weather service, marine service, environmental information service. And these we actually then connected with something that the Sustaining Arctic Observing Networks, an organization where I, again, also represent Finland, that put that in the description of myself. There, this kind of a international assessment framework was developed for how to see that how Arctic observations are useful. So there, they identified 12 different societal benefit areas, 170 key objectives beneath each of these areas. And we connected those services, the 6 different ones on the previous side on the right, we connected with all of these key objectives. And from there, you now have where does the invested thing, observation system, where does that end up? So in that sense, you could say, this is how much each SBA should pay for that system. We could turn it around. So that's the idea to get it for. But now, this was just the nicely organized meteorological and ocean kind of network. So this was practical, didn't take more time than a few months, and I could do that with a good team of experts from the Arctic. Now, if we would want to expand this into other in situ sources, which are non-WMO, I did find some good sources. There's an Arctic Observing Bureau that NSF have been paid for. At the moment, the search listing was not working in a way that I couldn't export the lists. Didn't practically help me, for example, to try to dig up something. Arctic Spatial Data Infrastructure, Arctic SDI, has a site, mostly just maps. There's an interesting thing that a company in Finland, Spatineo, was actually doing for the Natural Resources Canada, is kind of harvesting. So Spatineo in general just takes, I think there are about 100,000 OGC servers running in the world actively. So Spatineo is kind of polling them and seeing how well do they kind of like stay up, how well do they kind of like how fast do they serve the data. So from that, they are looking into that list that they have to find out who is from the Arctic. And so they found 6,300 or 400 services, about 330,000 records. But also there, the same problem with the bounding box. A lot of like latitudes or the bounding box is even defined differently, but there's not actually degrees latitude, but numbers which are like 60,000 or something. So very difficult to find there also what to take out the wrong records. And really there are over 100,000 spatial web services at the moment, which is not growing too fast. I think it was like over a year ago, it was 99,000, just 6,000 a year more. And this is, I think, the message, that we do have lots of data out there for in situ especially, but we have not very much of it behind a useful service that could also give you the access to the data, and then the searching would be in a uniform way. And we should actually get a lot of wide adoption to make this successful, that all that data would be useful. And the biggest problem is for these small in situ data sets, that they are really, for them, the hurdle to do a OGC service out of their small data sets, which maybe are not ongoing activities, just something that they did for a period, then they finished up. So we need to help them somehow. The crowdsourcing data set is also something that there we have a problem which is much more common to other areas of opportunity, like big data analysis of text and images. We should somehow see how we can add that also to the thing. So now the improvements. So there is, in the Arctic and polar data communities, there's actually this kind of schema or vocabulary to be put in place. So there's a lot of that already. The common semantics, but we need to put that in descriptions of these data sets. So when you have HTML pages about this data. We need to use something called microdata, and there are two different standards that could use RDFA and JSON-LD, that those would be needed to be added to those records. So then a search engine could find the things, and it would be more exposed to the world, because nowadays we have 2.5 billion or even more web addresses, so nobody will just accidentally find something, so they need to use a search engine. If the search engine doesn't know anything about the data set, we don't find it. And then there's a spatiotemporal asset catalog is a standard in development. It's currently at 0.6, but the idea there is with a very kind of short and simple JSON structure to define just the most important things. So what is a variable and their characteristics, then the spatial and time definitions. And then it's extendable, so if you want to define more, you can make a plugin and put it in there. So it has mainly born from Earth observation satellite data, but now it's also trying to get into this numerical models, 5-dimensional stuff. Yeah, and this catalog is really easy to turn into HTML pages, so that's then what the search engines would go through and find. But something similar is happening with OGC, the Web Feature Services Free proposal, I guess. I don't know what the timeline was for that to be finalized, but that's also trying in a very simpler thing. To move in that direction would actually be maybe the how to get to find those data sets and access those data sets in a part of it kind of question, and it would pair with this stack. So I think that's something that we should all look at and think that if we would put things there, because I think very ultimate goal is that we can find all the data, but we can also access it in smaller chunks. For the space part, it's very simple that if you would have to always take 1 gigabyte of file to be able to just look at a few pixels around your house, people will not do that. So we need to subset spatial and temporal extents and be able to then get that. And that's the conclusion. So we have to go from complex to simple, and in situ data cataloging dissemination would need a service that this data can be, let's say, put more. I think that's something where we should see that how can we in GEOS do something about that? Because I think that is easier done as one solution and then try to federate it in many places when to get everybody, let's try to do your own solution. That's maybe the main message. Thank you.
Okay, thanks, Mikko, for that good tour of going from crowdsourcing to non-WMO metadata and in everywhere in between. So we've already got now one challenge laid out for us for the GEO Knowledge Hub in terms of in situ data management. So that's very good. Thank you very much. Next, we have Bartolomeo Ventura from EURAC, the European Academy, and he has a PhD in physics. He's been with EURAC since 2010 and has some experience with doing validation of soil moisture retrievals from satellites. So with no further ado, Bartolomeo, it's yours.
Sorry. Good morning, everybody. And in my presentation, I will try to explain you why it's important to adopt standards, and in particular, how we adopt them in our data workflow using the OGC sensor web enablement. My presentation will consist essentially in 3 parts. First of all, I will describe you the problem of the absence about the standardization. Then I will show you how we use this standardization concept in our data workflow. And finally, I will show you a practical use cases in this initiative that is called LTSER Match MATSIA. So heterogeneous data is the starting point. We know that in the last decades, the market of sensors has grown quickly. We found sensors which are smarter and smarter, and they really has a low price. But the problem is that when I have to deal with very big data sets, which are all different, I need absolutely a standardization, because standardization will lead us to data sharing and interoperability. So the real problem is that we have a completely absence of standardization for input data. In fact, we can find different sensor and station, different data organization with respect to the same sensor, different data organization, and different same for input file. And sometimes it's also within the same sensor that maybe update its own software, something will change again. So the standardization concept is something that gives us the possibility to share data with multiple applications and users. And everybody here maybe knows about the OGC and the Sensor Web Enablement Initiative, which introduces standards. And this standard will have been adopted by us. And in particular, we used the implementation of the 52 North for SOS. And the web application of the 52 North use an API which let us to fill a database, a PostgreSQL database, using a methodology that are defined in the SOS standard. To explain how we use this standard in our methodology, I have to explain how we organize the data lifecycle, which is a high-level overview about the life of the data from the acquisition to the final sharing. There are different definitions of data lifecycle. This is the one that we used. And in particular, we acquired data collected by ground stations spread around South Tyrol, which is a region in the northeast part of Italy, and which are collecting data, physical parameters, and also images in RGB and infrared spectrum. These data are harmonized because it's not unusual that during the acquisition we can have gap data loss. So it's important to have a coherent data set, and before, let's say, move to the next step, it's important to evaluate that 5 dimensions, which are completeness, consistency, uniqueness, validity, and accuracy. Once the data have been harmonized, we can then organize them using the SOS standard. As I was saying before, the 52 North SOS provides a RESTful API, which uses these 2 operations, which are the insert sensor and insert observation. And if you have to deal with a huge number of data, it's important that these 2 operations are automatized, because otherwise you really are in trouble. In fact, the innovative part of our methodology consists in the fact that from the data provider or user point of view, we only ask 2 minimal interaction. One is the standardization of the input file, which has to follow these simple 4 rules, and the creation of what we call the configuration file, which is an XML file containing all the information that then will be used for creating the insert sensor XML file and insert observation XML file. And it can be seen as a raw version of metadata about this feature of interest. Once these 2 steps are fulfilled, the remaining part of the methodology is completely automatized, because by means of an XSLT transformation, we can use the configuration file to create the XML insert sensor file, which will insert in the database station, and the template for insert observation XML file, which will be updated using the information, so the ground measurement written in the input file. We also developed 2 versions of the insert observation operation. One that is we called serial, and the other one that is parallel. The difference is in the fact that with the parallel you can speed up further the process, and we also did a small benchmark analysis where you can see that if you have a number of stations which is greater than 10, you can save up to 80 minutes in uploading data to the database. Once the data are in the database, researcher or simple curious can really analyze them, and they can use the RESTful API. And in particular, we developed also an R package that we call the Mona Lisa, which can communicate with SOS API and give you the chance to have a look on the data that are in the database. And since it is written using the R code, users can add their own code to customize the output, so they can get plot, statistical analysis, JSON files, and whatever they want. Once the data are in the database, they have also to be shared. This is why we developed a graphical user interface. This web application communicates with SOS, and using a series of menus, you can ask to it and get first information about the data available using simple instruments, which will let also for those that are not that expert in writing queries to get information about the data available in the database. Another important aspect is the creation of the metadata. Just a few minutes ago, we were talking about metadata. Metadata is something that is really important, and unfortunately is not considered that important. I mean, just a small parenthesis, I've seen that researchers used to spend months or years for one publication, but they don't want to spend 10 minutes or more to write metadata about their own data. So it's important to use metadata because they will let us to save time. In particular, in our methodology, we use the XML configuration file and another XSLT transformation to get a final version of the metadata, which is compliant with the ISO, OGC, and INSPIRE standard. But since the XSLT transformation is done by the data provider, for example, you can get the standards that you want, or or in any case, it will depend on the requirements of your specific project. So you can change the XSLT processor, you can get a final version of the XML in the way that you prefer or is asked. In particular, the fact that we are able to have metadata which are standard give us the chance to integrate this metadata with GEO's platform. In fact, now if you search for SOS and URAC as keywords, you will get some of our in situ station, and this is something that has been possible because we are using standards. From their side, it was only a matter to organize the harvesting, and then the metadata are there and are available for the community without any further operation from their side. And this is one example that you can get using the GEOS portal. The methodology we used has been tested on this initiative, which is in the framework of a larger initiative, which is the long-term ecosystem research, in which a lot of European countries are involved. In our case, the LTSER MATSIA is dealing with the analysis over this valley in South Tyrol, and here you can see the area that we are investigating and the station from which we are collecting data. And up to now, we collected more than 80 million observations from 30 ground stations corresponding to 500 sensors. So you can easily understand that to have an automatic procedure to handle this number, it's fundamental. In our case, we use SOS for sharing the collecting data using the sensor web enablement standard. We have only to write 30 configuration files, and then the system is completely automatized. And because of some requirement from of the project, we are able to upload data in a near real time. In particular, every 15 minutes when the new data are available, the system is able to upload automatically everything without the interaction of the user. So what is important in this case that we are using standard, but user can even don't know anything about them because it's something that is blind to his or her eyes. So the conclusion is this one. First of all, this is my key message. The adoption of the 52 North SOS implementation and the integration of a specific tool can automatize observation, uploading, and sensor registration with the less effort possible by using sensor web enablement standard. We create an OGC standard compliant methodology, which is flexible, open source, and that can be customized. Data are shared in near real time, and it can be for sure improved because source code are available on a Git repo. So what GEOs can do, in our opinion, is to push more and more towards the use of standards, because this will avoid the loss of many terabytes of data duplication, and maybe what is even worse is what now are called the dark data, which are the, let's say, the dark brother of the data, and which are even bigger than the normal data that we use to handle every day. For the future, we would like to develop a more user-friendly configuration for creating the configuration file. We are also developing a driver to connect the OpenGEO API to the SOS API. And we are also investigating the use of Stack for handling metadata. This is it.
Okay, thanks, Bartolomeo. That was interesting. One of your final conclusions there was that GEO should push more towards the use of standards. I mean, any of you who have been around GEO for a while know that GEO has been mainly about finding, not saying what to do, but finding ways to adapt to what's out there. And interoperability has been an issue that's been around GEO since the beginning. So maybe it's interesting to maybe revisit that position and see if GEO should be a bit more proactive in terms of recommending standards, especially in the in situ realm, where we don't have a coordination body like CEOS for space-based observations. Okay, thanks very much. Next up, we have Peter Hunter from the University of Stirling, who's a senior lecturer at the university. He specializes in the development, validation, and application of remote sensing methods for monitoring and assessment of inland, transitional, and coastal waters. So transitional, just for those of you who don't know the parlance, transitional means going from, say, open ocean to the coastal zone, where there's, estuaries, for example, where there's a transition in several parameters. He's been involved in the development and validation of global Earth observation water quality products throughout the UK through the Global Lakes Project, and he now works on a series of Horizon 2020 projects. And I think he's going to tell us something about the Limnades in situ optical water quality database. So, Peter.
Thank you for the introduction, Doug, and good morning, everyone. So, yes, what I'd like to talk about this morning is basically some of the requirements and challenges for in situ data in relation to the validation of global inland water quality products. But I'm going to start, given the audience and their background, a little bit of information on why we should be interested in lakes. Well, first of all, there's an awful lot of them, something around about 117 million lakes on Earth, and that's something we only know because we're able to count them from using satellite data. But in spite of their number, those lakes only cover a relatively small proportion of the Earth's surface, a little bit under 4%. But in spite of the fact they don't cover much of the Earth's land surface, they are vital ecosystems. They provide a number of important ecosystem services to society. That's reflected very much in the SDG 6 for clean water. They also play a very disproportionately important role in global biogeochemical cycling and climate regulation, particularly because they're conduits and hotspots for carbon transformation. They also provide a lot of methane to the atmosphere as well. And they also are one of the most fragile ecosystems we find on Earth, and their status is threatened by a whole range of pressures, from climate change through eutrophication to brownification, which is the increasing colour caused by inputs of dissolved organic carbon. And more recently, we're starting to appreciate the impacts of things like microplastics and other forms of pollution on these fragile ecosystems. In spite of their importance, there's actually very few lakes globally that are monitored. As part of the Global Lakes project that I'll mention later, we estimated this at less than 1,000th of 1% of lakes have in situ data. So there's been a long-term interest in developing Earth observation methods for producing global water quality products. But this has historically been a bit of an intractable challenge, and the reason why it's so difficult is because what we see with lake ecosystems is they exhibit high in-water optical complexity. They're also very close to the land surface, so we have adjacency effects, and overlying those lakes we have very continental type atmospheres, and those issues add up and total to the fact that it means that our algorithms that we develop to produce water quality products generally have quite limited transferability in space and in time. So ourselves at the University of Stirling, with colleagues at the Plymouth Marine Laboratory and other groups working internationally, have been trying to solve this problem for a number of years, and really the solution, or one of the solutions that we've come up with recently, is the development of an adaptive processing chain where we're using an ensemble of algorithms that are tuned to specific optical water types, and that's shown in the figure on the right-hand side of your screen there. So as part of the Global Lakes project, we were able to identify about 13 different optical water types globally, and then we tuned a series of 4 different algorithms to optimize the retrieval of water quality information across those different lake optical water types. You can see the validation results there in that plot. And that's the processor that came out of that research is called Colymnos, and in the Global Lakes project we use that to produce 10-year time series of water quality data for about 1,000 of the world's largest lakes globally from MERIS data. More recently, that same processor, Colymnos, has now been used in an operational context for processing of Sentinel-3 Ultra and Sentinel-2 MSI data. And that's been developed through a Horizon 2020 project called EOMOS. It's also the processor that's behind the water quality data in the Copernicus Land Service and will contribute to the Lakes CCI project funded by ESA. I'm not going to go into the technical details of the process, but happy to discuss that after this session. That's just an example of some of the water quality products that we've produced using Colymnos. This is the data portal that we produced for Global Lakes, and we have a similar one for the EOMOS project as well, where users can go and browse the various water quality products that we've produced by parameter and by geographical region and time period. What we've done with those data that we produce for these projects is try and produce the first global assessment of water quality status from space, and that's reflected here. So this is 1,000 or so lakes that we studied as part of the Global Lakes project, and they've been classified according to their trophic status, from the low productivity, high water quality oligotrophic systems to the more impacted hypertrophic systems there from the blue through to the dark green colours. So those water quality products that we've produced with Global Lakes, they represent roughly about 50% of the world's surface water. So that's how much of the surface water extent that we're covering at the moment from through these data products we produce through Global Lakes. Now, obviously, the in situ data are vitally important. We need in situ data, firstly, to optimize the algorithms that we use to produce these water quality products. And there it's really, really important that those in situ data represent the full range of optical water types. If we're going to generate a global product, we need to ensure that our products are performing well, not just for one or two of those optical water types, but for the majority, or in fact, for all of those optical water types. We also need in situ data to make sure that the performance of our processor and the products that it's produced and the uncertainties associated with those products, we need to characterize those over the lifetime of satellite missions as well. So it's not a one-off process. It's a continual process of validating and characterizing uncertainties associated with those products. And in spite of the ability to monitor a lot of these systems from space, there's always going to be gaps in the EO data records, whether that's spatial or temporal. So we still need in situ data as well to help fill some of those gaps at times. So in situ data are really critical to our ability to demonstrate these products are firstly accurate and to characterize their performance through time and space. So as part of the Global Lakes project, we set about developing an in situ database for the validation of inland water quality products, because at the start or the outset of that project, there wasn't a database available. So we did this really as a kind of a side project alongside Global Lakes, where we contacted as many different researchers and institutes as we could that we knew might have data we could use to validate our algorithms, and we pulled all that data together into one centralized database, which we called Limnadis. So we then would see Limnadis as a community-owned database, although it is managed by ourselves at the University of Stirling. And currently it's about 30 different contributors to that database from across the world, and it's shown there in the map on the right-hand side. And currently we've got about 60,000 measurements in Limnadis. Mostly measurements of chlorophyll A, so that's a kind of proxy for the kind of productivity of the water body. And those data cover about 1,500 water bodies in total, although a slightly smaller subset of those water bodies actually have radiometric data for the validation of satellite radiometry. So Limnadis was established as kind of a spin-off from the Global Lakes project, but more recently we've got a small amount of funding through the Horizon 2020 Monocle project, which is focused very much on the development of in situ instrumentation and protocols for satellite validation. We've been developing the Limnadis database through that project, largely using open source software. This is trying to develop basically a new back-end, a new interface to the database, so it's more user-friendly for the community. I'm not going to go into the technical details of the database, but one of the kind of the main improvements we are making to that database is developing a real-time connection to the CLIMNOS processing chain, so we can validate our algorithms on the fly as soon as new in-situ data are added. And we're also looking into the possibility of developing a connection with SNAP, so users of the SNAP software can validate their own algorithms using data from Limnadis. That's just a screenshot of the interface that we've been developing. So you can search for data by geographical region, by time period, and by parameter. And this slide really just demonstrates why it's so important that we have access to in situ data for the validation of these products. This is an example taken from Loch Ness. It's the largest lake in the UK. And Loch Ness is one of the lakes that we have really good in situ data for. So the plot on the bottom of your screen there shows the satellite estimates of chlorophyll A concentration in red, and then the in situ data is plotted in blue. And you can see from the main part of the year, we actually do quite well from space. There's good agreement between the in situ and the satellite data. But you can see in the spring period, we greatly overestimate the in situ chlorophyll A concentration because our algorithms at that period just don't perform as well as we'd like them to. And the point I'm trying to make here is that in the absence of good in situ data, we wouldn't be able to recognize that. We wouldn't know when the limitations of or some of the limitations to the products that we produce. So high frequency, high quality in situ data are really vital to understand the uncertainties associated with these products. And that's an issue, because if we look at the availability and the global distribution of chlorophyll data that is held by Limnadis, there's a very strong bias. The vast majority of those data come from Europe and North America, and there's large areas of the world where we have very few in situ data. So you can look there in parts of Asia and Africa. We don't hold any data at all in Limnadis at the current time, or very few data. That's not to say those data don't exist, but if they do exist, we don't know where they are, or we haven't been able to access them and use them for validation. Why is that bias such a problem? Well, if we go back to this global map that we produced during the Global Lakes project, here those 1,000 lakes are now coloured depending upon the trend that they exhibit in the chloroflake concentration. So those lakes that are coloured here in the kind of yellow and orange colours are showing very little change over time. Those coloured in blue are showing decreases in chloroflake. Those coloured in green are showing increases in chloroflake. And if you look to North America, you see there's a large number of lakes, but proportionally most of those lakes aren't exhibiting particularly pronounced changes in chloroflake. Whereas if you look to Africa and the Rift Valley lakes, you see there's fewer lakes there, but proportionally more of them are actually exhibiting significant trends in chloroflake. Some of those systems we're seeing increases in chloroflake, which is indicative of probably declining water quality. In other lakes, we're seeing a decrease in chloroflake, which in some situations might be good, but it might also indicate declining productivity of the system. And this is an area where millions of people are dependent on those systems for their drinking water, but also it's also one of their main sources of protein because they're important fisheries. So we're able to capture those trends from space, but we don't have any in situ data to validate those products for those African Rift Valley lakes at the moment. So although we can see those trends, we don't know how accurate they are. And that's the issue with the bias that we see in the availability of in situ data at the present time. The bias is not only geographical, but it's also bias in terms of the type of system that we've got in situ data for. If you think back to that map I showed you earlier, showing the trophic state of the 1,000 of the world's largest lakes, the vast majority were oligotrophic or mesotrophic in character, but actually our in situ data is very much biased towards eutrophic systems. And partly that's because historically a lot of projects that were funded to collect in situ data, we were interested in high biomass systems where we had harmful algal blooms, and that's very much biased the in situ data we have for validation towards those systems. So we have this geographical bias in our data sets, and that means that often where EO has the biggest potential to contribute and the potential to have the most transformative effect on the way that we monitor water quality, those are actually the regions where we have the poorest understanding of the uncertainties associated with our data. And also, as I mentioned, we have this bias towards very high biomass systems. Another issue that we have that's already been mentioned is that the fact that a lot of the in situ data that we have available for validation have been collected and processed using a large variety of protocols, both in terms of the data collection and also for the processing. And often these data have been collected with very limited metadata. So it's often very difficult to know what the uncertainties on the in situ data are as well. And that's something we need to tackle. So I very much see that a role here for AquaWatch in terms of trying to coordinate community efforts to ensure that we get more in situ data from those areas where they're currently quite data poor, as well as perhaps readjusting the focus towards those optical water types or lake types where we have less in situ water quality data for validation. The other point as well is that in situ validation campaigns are often funded through short-term projects or indeed soft money. So the continuity of in situ observations is often relatively poor. And as I mentioned earlier, it's really important that we don't just do this validation work as a one-off effort. It really has to be undertaken throughout the lifetime of these missions. But at the moment, there's not the funding structures in place to ensure that we can continue to collect in situ data to undertake that validation work. There are some new in situ technologies that are helping there. So ourselves at Stirling and various other groups internationally are starting to look towards autonomous systems. For example, here the radiometers that we've installed on Loch Leven to collect measurements of reflectance for the validation of satellite radiometry, as well as measurements of aerosol properties as well, using some photometers. So this sort of instrumentation is becoming more common, although it's still very much something that you find in North America and Europe. So it's not really helping us fill the data gaps in other areas of the world. And also we're starting to use citizen science as well as a way or a tool to collect in situ data. So the example there is from a smartphone app developed by the Centre for Ecology and Hydrology in the UK, where citizens can record the occurrence of harmful algal blooms. And we're now using that data to validate some of the water quality products we're generating for the UK. So these new technologies and tools can certainly help us collect more in situ data for validation of satellite observations, but there's still some substantial challenges that remain. So in terms of my take-home messages then, I hope I've convinced you that inland waters are indeed vitally important, indeed sentinel ecosystems providing many benefits to society, but they are threatened by a number of different stressors. Monitoring and assessment via Earth observation is, at a global scale, is certainly now feasible, but we really do need rigorous algorithm calibration and validation. And that is an issue because the availability of high quality in situ data is very limited for some geographical regions and indeed some lake optical water types. So Limnadis is really an answer to this challenge, and it's a community-led effort to provide centralized in situ data access and to help standardize the protocols that we use to collect this data. So hopefully we're moving in the right direction, but there's still a lot to do before we can say with certainty just how good some of these global water quality products are in fact. And I'll leave it there. Thank you very much.
Okay, thank you, Peter. Again, the take-home message that I have, despite the ones that you showed up there, is the importance of in situ data for algorithm, validation. If you don't know how the algorithm is performing, then what good is it? And you need in situ data for that. Okay, our last speaker is Rick van den Bosch, and apologies for the typo in your name in the agenda. Rick is the director of the International Soil Reference and Information Center, which is a service provider to the international community in the field of soils. It provides training and capacity development in soil measurement, soil data management, and soil mapping. Rick is the director of the Institute for 2 years now, and before that he worked for 25 years at the Wageningen University and Research Center in various research and management positions. So Rick, all yours.
Yes, thank you for the introduction, and apologies for the organization that I didn't use the format that was provided. I only discovered that this last evening, late in the evening. And also there's something wrong with the font that is not captured by the beamer, but let's see how far we get. ISRIC is the International Soil Reference and Information Center. We are based at the Wageningen University campus, but we are an independent foundation. Founded in 1966 upon recommendation of the UN, because people wanted to have a place where they could go to learn about the soils of the world. And the Dutch government has made a pledge to make sure that such an institution would be funded, and they still do so. So we are still there, and we produce and serve quality assured soil information together with our partners at global, national and regional levels. And we stimulate the use of this information to address global challenges through capacity building, awareness raising and cooperation. So we are really the institution in the world that covers the entire world in terms of global soil information. And we work according to open science principles wherever that is possible. So the topic of my presentation here today is soil organic carbon, and why should we bother about soil organic carbon? First of all, soil organic carbon contributes to various important soil functions. It regulates nutrient cycling, it regulates water, it can help in climate change adaptation, climate change mitigation. So for everybody who's using the soil organic carbon is one of the most vital aspects of that soil. So it's important for climate change adaptation. On the other hand, it's also important for climate change mitigation. Most of you shall have heard about the 4 per mil initiative by the French government, claiming that if we increase soil organic carbon with 0.4% on a yearly basis, we can offset all current CO2 emissions, and current is then 2015. So there's a huge potential, if we manage that soil properly, to do something about climate change. So it's important for climate change mitigation. Then it's a huge stock. if climate people talk about adaptation mitigation in the AFOLU sector mentioned yesterday in one of the speeches as well, often people talk about the vegetation. But if you look at the stocks in vegetation and atmosphere and in soil, you see that the total stock of carbon in the soil is double the stock of the vegetation plus the atmosphere. And then in those assessments, we usually don't take into account the permafrost because data are not very much available for that part of the world. But a recent study showed that in the permafrost regions in Canada and Russia, there's another like 1,500 petagrams of carbon available. So if you add those two up, it's 3 times or 4 times the amount of carbon in vegetation and atmosphere. So it is a huge thing. And we can lose, if we lose a lot of that carbon, then that will be a disaster for climate change. But also, there's still a lot to be sequestered there. So that's one of the reasons. Okay, and then the third reason why, or the fourth reason why carbon is important is for land degradation neutrality, mentioned yesterday also. So soil organic carbon is one of the sub-indicators of this 15.3 indicator for land degradation neutrality. So now we've seen that carbon is important for climate change adaptation, mitigation, land degradation. So who's monitoring at global scale? Well, nobody. There is no global efforts and very, very few national efforts to monitor this huge carbon stock. And that's the issue. So how do we get estimates of soil organic carbon on a global level? We do that through digital soil mapping, combining available in situ measurements with remote sensed EO Earth observation products to predict soil parameters. And basically at this point in time there are 2 global products predicting soil organic carbon. One made by the Global Soil Partnership and one made by ISRIC. And I will dive a few slides into that product that we produce at ISRIC. So what is soil grids? It's a global grid at 250 meter resolution, predicting soil type and basic soil properties at 7 standard depths. It's derived from in situ soil observations and remote sensed products. Developed in an open science process, so everything is available in open data, open source, and open journals. We include in our estimation also the inaccuracy estimates, so we can see where on Earth the estimates are more accurate than on other places. And this product is used for national reporting by the countries in the LDN reporting process last year. The last bullet I changed yesterday evening because there was something like a lot of downloads. I thought, well, let me put here, the next version will be cloud-based because that is the real future of what we're going to do and the next version will be released this summer. So that strategy, that digital soil mapping strategy, we first started with multiple linear regression and Grieger methods. But the last 4 years, we've used machine learning algorithms like random forest and gradient boosting, and that has increased the predictions a lot, as shown by cross-validation statistics. In terms of in situ data points, we have now, very similar to the previous speaker, 150,000 soil observations in one database. And each point on this map is a database in itself because it covers various parameters and various depths. So it's a real profile description for each point. So we have 150,000, and also here we are dealing with the harmonization, standardization. Everybody's using his own methods, his own chemical analysis, its own naming, its own ways of projection. So there's a lot of issues to get these data into a form that we can also compare the data with each other. Then we use to a maximum of about 150 covariates for the predictions. And then we get a database, 7 different depths, and about 10 different parameters. And if you go to soilgrids.org, you can, on the right-hand side, you can choose your depth, you can choose your parameter, and sort of view what the data are like. So to give you an example, here is the soil organic carbon stock at 30 to 50 centimeters in ton per hectare for Indonesia. But what are the limitations of this product? Well, first of all, limited in situ data, 150,000 points for the entire globe. The most important limitation is that these data come from different decades. So we are sort of having a mixed bag of data from different decades, and we sort of assume that that also reflects the picture for today, which is of course not correct. But if we disaggregate those data for decade by decade, then we don't have enough information to make reasonable predictions. There's a huge limitation in terms of standardization and harmonization. Sometimes we get data in and we plot them on a map and 30% is in the ocean. So then we have to go back to the descriptions of those soil profiles and say, okay, this was 150 meters east of the village in this country, and then we sort of assume new coordinates. So that's the type of issues that we have to deal with if we are standardizing and harmonizing these data sets. And there are very, very limited situations where people go back to the same place in time and measure soil organic carbon over time. So my conclusions is that, the soil organic carbon represents a large carbon stock, very significant and important. Quantification of that carbon stock is important for targeting interventions in the landscape and to perform impact assessment. It needs to be monitored, or at least supported by in situ measurements and not only remote sensing. And the difference here is that we also have to look into the depth, and that will never be covered by remote sensing. So we really need to dig holes in the ground. The technology is available, and field work in terms of soil science has never been cheaper as now because of proximal sensing technology, so we can escape from expensive wet chemistry methods. So my conclusion here is that we need to facilitate countries to design soil carbon monitoring programs based on current global stock products, so we can, the design of those programs can be based on where there's available data already available, where the predictions are accurate and not accurate, so in order to add maximum value to the current products and run them according to agreed standards for sampling, measurements, and data management. And the problem here is that the technology is there, people are willing to do this, but of course it's the funders are, these programs are not easy to get funded. So I think basically my message here is that the soil scientists are not used like most of you people. The data come in on a regular basis, that someone makes it ready for analysis. And that's a new terminology that I learned yesterday. So you can easily go to a data cube and get all this data and start doing your analysis. Here the situation is different. We are struggling with data from the 70s, from the 80s, trying to make the best out of it. But of course, if you really want to get a proper picture of soil organic carbon in the soils of the world, we really need to go back to the field. Thank you.
Okay, thank you, Rick. So we've heard several messages here from the four presenters. We've looked at in Mikko's presentation. We heard about citizen science and the challenges that are related to that. It seems like the app that you have is a pretty good way to go. But perhaps bearing in mind that the theme of this particular session is what are the needs and challenges of handling in situ data and what should GEO's role be with respect to that. Perhaps there's a role that we need to look at in terms of helping citizen science initiatives. And then we've heard several times the call for standardization, harmonization of collection and data exchange with in situ. We've heard about in situ, how important in situ measurements are, both in terms of water quality, algorithm development, and also soil organic carbon. And then we had one example of a data life cycle that could respond to some of the needs for standardization and harmonization. So with that being said, we've got about 20 minutes for some questions and answers. I have here on Slido a few questions. I think I'll start with those, and then maybe we'll do 2 or 3 of them, and then we'll open the floor for any questions you might have. So the first question here is directed to Miko from Gilberto. So how relevant for in situ data providers is it to adopt the schema.org and JSON LD formats? How do you compare XML with JSON LD? So a technical question.
Well, thank you for technical questions. I like them as well. I would say that this is more a question of that the XML is like where many standards at the moment have a better kind of definition. But because of that, that they have shown that not too many are adapting it, or that there is a significant amount of people who didn't adopt it. I think JSON is just trying to make it a little stepwise simpler for some things and not be so strict. That's why it is useful to get there. The schema.org question is really that I think that we should be aware of the whole world in internet terms more, and that is that search engines are really important nowadays for all kind of traffic. Traffic means success. So if you go to business and they want to invest, they are interested of how popular is your website, how many subscribed users, how many identified users do you have. These kind of questions we should also be able to kind of like be aware of and be somehow answering to. And for that, I think we need to be found better. And that means that search engines need to find us. Well, schema.org is actually made by search engine companies that, hey, if you would just write that onto your web pages, we could find easier the significance of your thing. And especially for something like data sets and very, let's say, like technically structured actions, it is very useful that we would do that. But of course, this is again something extra to do. But in this case, I think it's not too much to write extra. So we should at least start doing that. And then we find more useful it. Because I think we have to be very clear on that when the funding issue, for example, for the soil case, is very difficult. This has to come from a very simple thing that topic doesn't really reflect, like it doesn't resonate on so many people's minds. So how do you get that to resonate is to just get much more of that message out of there, that's super important. We could do a significant thing for climate change with that, but we need to just like market. And we are boring organizations that we don't pay for marketing, like we don't pay Google that, why don't you just send everybody to look for soil carbon things? Because that costs. But we should be at least helping that system to anyway find us better. And I must say, the Finnish Met Institute, we are really bad on this. Our open data, which we have had since 2012, you can't find them on Google or Bing or whatever. It's really bad. And we have, let's say, self-analyzed the system that's exactly because we haven't made it at all nice on our OGC services, that the description things are many times in Finnish. They are like definitely not saying that this is, like we have a very mixed setup there, so it's bad. So that should be changed, and well, there's a working group inside our house to try to improve that. So that's why I can say that from a certain point of view, this is exactly what would be helpful. But it's an extra task again. But it's like the 30 configuration files. It's simple to fill them. I don't think so. Like for many, that's exactly why, like filling them is also filling them correctly. That you therefore bump into this. And their JSON thing is maybe a little bit like it's not as much, and you don't have to be necessarily always so kind of syntax correct. But when you fill in something, it actually starts already working. And you can then build it up better. That's probably where the technical answer goes to why I think, and I like more to look at JSON stuff and do something there when XML, even if I accept the history of XML being like a grail, but it wasn't.
Okay, thank you. A question from Gilberto to Peter. What will happen to Limnades in the long run? Would you consider having a data backup on a certified repository such as Pangea, or what's the outlook for Limnades?
Yeah, thank you for that question, and it's a very good one. At the moment, that question remains open, really. We have funding to support Limnades for the next 3 years. After that, we don't know exactly what will happen to those data, whether that's something that could be taken on by another database. There are obviously databases out there for ocean color data, and they are funded, but the data that we hold and some of the I would say the protocol requirements for those databases don't necessarily mesh with those that we employ for Limnades. So it's not a straightforward task just to move all the data that we hold in Limnades to one of those existing ocean color databases. So I think at the moment our view is that Limnades is something that we would like to continue, and we are actively seeking funding to support that because we think it's a particularly useful resource for the community. That's certainly the message that we've got from the collaborators and those individuals who are using the database. But the long-term, I guess, management of that database and the funding to support it is a question we've yet to probably answer, rather.
Okay, thanks. And then there's a question here for Rick. Let's see, where did the question go? Okay, what do you see as the primary barrier to a broader collection of soil organic carbon data? Is it funding? Is it a lack of interest in the countries? How can GEO assist?
I think it's a combination of the two that you mentioned. Soil organic carbon is not as sexy as counting birds or butterflies, and it's under our feet. We have a soil museum at Isrik where you can see 120 soil profiles displayed. So you see the depth and the colors, etc., etc. And we get people in the museum saying, "Oh wow, I never realized that soils had a third dimension." So, and those are policymakers. So imagine that is one part of the story, and the second part is funding, but it's maybe a direct result of the first thing that I mentioned. So it's really the technology is there, in the 70s and 80s there were a lot of cooperation projects that were funded by Western countries in Africa and Asia that yielded a lot of soil information, but that has stopped as well. So there's simply not a lot of programs that are funding these kind of activities. And how OGC can help, that was the last part. GEO, sorry. Yeah, I think it's about advocating and maybe also about fundraising. I don't know. Maybe we can discuss that a bit more in detail.
Okay. Now I'd like to open it up to the floor. Does anyone have a question that they would like to ask our panel here? Anything come to mind? Okay, yes.
Hello, my name is Jean Almeida from Brazil. Actually, I have two questions. One is for Rick, and how the great products compare to the FAO products in terms of resolution or data itself. And to Peter, if there's in the database, if the reservoirs are included or aim to be included in this analysis, especially because there's a lot of maybe more in situ data in reservoirs than in lake itself, especially in developing world. Thank you.
Yeah, thank you for that question. The other product is the GSP product. So made by the community, by the Global Soil Partnership community. And the person who is actually managing the process is sitting right next to you on your left-hand side. So you can shake hands. And the products are a bit different in nature. The GSP product is a bottom-up product where countries made their own global soil organic carbon maps, and then it was stick together and brought together. There's more in situ data underpinning that product, but there the harmonization, standardization is a big question mark, and I'm looking at Yusuf if I can say that. And the ISRIC product is more like a top-down product where we have sort of tried to standardize and harmonize the data that we have as well as possible, and then use one model or derive one model with the training data for the entire globe. So they are very different in nature, and I think they can be very useful both next to each other. And in terms of accuracy, I cannot answer that from here, which one is more accurate. It's always a very, very difficult question. Maybe Yusuf and I should write a paper about that one day. Was that your entire question, or was that? Yeah, okay, thanks.
I think the question that was directed to me was about the inclusion of reservoirs and the availability of validation data for those. Within the 1,000 lakes that we produce water quality products for through the Global Lakes project, a number of those water bodies are drinking water reservoirs. Although those that were man-made systems were excluded because that project was very much looking at the impacts of global environmental change on natural water bodies. But you're quite right, there are a lot of in situ data available for reservoirs, but the problem there is that our stipulation is that the data are publishable in an open forum. So certainly there's a case in the UK and many other countries that the data collected by water utilities companies, they sometimes are happy to share that data because they're interested in the validation of the products that we produce, but they won't allow us to openly publish those validation results because those data have there's issues around the release of those data. So that's a problem and again a restriction on the availability of the data that we have for product validation.
Well, I actually have a comment to Peter in a sense, because seeing that you didn't have Finland on your map of lakes and we just have also 1 million or whatever, just it depends on how do you define, how big do you have to have a water body to call it a lake. But I think we do have probably 100 or so stations that data is freely and openly available. Talk to Pekka Hurskainen from the Environment Institute because they have hosted it for a long time. But I do know what your challenge will be. We have too much data in Finnish. So please employ someone to do some translation, and then you get into that. But this is a good reminder of us how simple sometimes they are not like huge difficulties to sometimes to get this better. But I think the big point is that we need better to network the operators of all these activities across the globe, and that will also enforce better standardization, better kind of access to each other's data sets will come also from the work that we are just a people network, and I think that's where GEO will surely try to do something.
Yeah, thank you for that comment. And it's good to know there's data available for Finland, which I think we suspected there would be, but it's, as you say, it's finding those data and speaking to the right person. So this is a useful connection that we've made sat up here. So I think the map of sort of global distribution of in situ data, there are countries on there that have data that were not that are not included in LIMNADIS certainly, but I think that does reflect the general pattern in terms of there's a very strong bias towards Europe and North America in terms of data availability. But there are issues, as you mentioned. So we've been grappling with the Swedish monitoring data as well, which is in Swedish and makes very little sense to us in the UK. So translating that data into LIMNADIS and going through the process of quality control and developing the metadata records for that is difficult when the data are not in your first language. And I totally agree with the point about GEO. I think there's certainly a role it could play in terms of making those connections so that we're able to discover where in situ data are and able to make those data available as a resource for the whole community. I think that would be a really positive thing that we could do going forward. So.
Okay, I have, all right, one more question, Bob.
Bob Chen. Actually, to follow up on Limnady's question. I was curious, the system you developed for people to submit their own validation data, did you design that from scratch? Did you borrow it from somewhere? Did you review what was out there? Any comments on, how transferable it is to other groups that might want to collect scattered validation data, like on soils or whatever else?
In the sort of the first version of Limnady's, we really developed the back end and the user interface from scratch. But subsequently, through the Monocle project, we've gone back to the drawing board a little bit, and we're now developing a sort of a more OGC compliant interface and back end, which is adopting approaches that are used elsewhere for ocean colour data. So we're working very closely with colleagues at the Plymouth Marine Laboratory on the development of that particular database. And if you're interested in the specifics, I can certainly put you in touch with our techie guy who's involved in the construction of that database at the present time. But that's not my particular area of expertise.
Okay, we're approaching the end of the session. I'd like to ask one more question from Slido to each of you. So no more than 1 minute in your response, and then we can be out on time. This was a question again from Gilberto to everyone. What happens when standards do not work or there are better alternatives? And we've heard several times due to the heterogeneous nature of in situ measurements and, they're hard to find and so forth. We've heard the plea for harmonization, standardization, and so forth. Well, what happens when that may not work?
You get vendor lock-in. This is a Google thing that they say, we hate standards, we just do our thing, and then it works, and everybody should use it. I think this is, from that very simple perspective, I think principally already a problem, that if we would just go after solutions here and there, we will not have a cross-disciplinary solution, which I highlighted that's especially a problem because even just semantic standards have been designed many times from one sector. They are not therefore like taking into account other things from another sector. And we should get to that point. GEO should work for that. And there, I think then it is about standards, and standards can be this small or they can be this big, and we should go for those small ones. Thank you.
Okay, in my opinion, I can say that if standard could fail, and it could happen, we can improve them. Just to make an example, for satellite images, raster images in general, there was in the beginning the ISO 19139 standards that then become 19139-2, and now there is the 19115-3 standard. And why there has been this evolution? Because in using it, we realized that maybe there are some missing information that can be useful in other fields or for other important information that can be fundamental to have in metadata. So if something is going to fail, this can be improved, but this does not mean that they have to be then abandoned. Otherwise, we will always be at the starting point. Everybody will do whatever he wants, and then it's easy to find a situation like this one, that where people didn't know each other, that one has data, and only because maybe if probably, but correct me if I'm wrong, if they have their own metadata in a certain platform, they can search for them and they can see, oh, okay, there is this other community that has this data. Why can I contact them? So it's important that if we have a place where all the information can be put all together in a similar way, everybody can infer from that place.
I would add to that, in relation to standards for metadata, obviously the absence of those standards greatly reduces our ability to reuse the data. And to understand some of the uncertainties associated with the collection and processing and inventory of those data. Specifically in relation to in situ observations, it's a real challenge, and thinking again about water quality here is that in some cases there are no accepted standards for certain measurements. and actually some of the in-situ data collectors are very much welded to a certain methodology because it's a methodology they've always used, and they've used it for many decades, and they don't want to change their methodology because they want comparability with their own data sets first and foremost. They're not so worried about us being able to validate our satellite data and comparability with other in-situ observations. So in that case, it becomes less an issue of trying to harmonise standards, but just understanding what methodology was actually used and what the uncertainties associated with that methodology are, so we can understand a little bit about the in-situ uncertainties in relation to those that associated with our satellite products.
Well, what you just said about the in-situ measurements is absolutely valid for soil organic carbon as well. So it's about standards for sampling, standard for analyzing the soil samples. That is the most important. Otherwise, you're comparing apples with pears and you get products that don't make a lot of sense. So that kind of standards are absolutely necessary.
All right, thank you very much. That brings us to the end of the in situ session this morning. Let's have another round of applause for our panelists. So I've been informed that the room is set up downstairs. Well, the entryway is set up. There are some banners, some of our GEO banners like these have been placed down there. So you are instructed to now go down to the ground floor where you came in and find the banners and position yourselves between them for our photo. And then we'll be back, then come back up for the coffee, which is in the usual spot as it was yesterday, and we'll start again at 11 o'clock for the next session. Thanks very much.